Okay, today we are going to introduce how to modeling and doing some calculations for our PMU's device. Okay, so what we will do here is first we are going to talk about the piezoelectricity and how it make a device called the piezoelectrical micro machine ultrasonic transducer. And after that, we'll introduce the analytical equipment circuit model, which is the main focus of this chapter. Okay, so the purpose of doing that is trying to simulate PMU device without using a finite element software like console. Okay, so by doing that, you can quickly calculate and estimate the resonance frequency and the displacement of the device you decide. Okay, and also you can quickly scan the parameters to have a quick view about what will affect the efficiency of your devices or what kind of signals you have to choose. Okay. We will also introduce FEM a little bit, but it's just for confirm the analytical equipment circuit model. Okay, so typically for circuit model, it's like what he's mentioned. He's trying to explain physics phenomena with electronic circuit. Okay, so you will see that's actually like what's the circuit we usually see in electronics in electronic circuit courses, but just instead of represent the current or voltage, we will convert it to like a displacement, like a damping ratio, like a vibrations. Okay, so that's a difference between them. Okay, and then we will talk about like we will compare the simulation result with analytical model and the finite element method to see how it would be different. Usually we can base on this to modify our analytic model, or we can also do something like we characterize our device and correct both FEM and the circuit model together. Okay. So first about piezoelectricity. So I think you all familiar with that. Is that when we apply a voltage to a piezoelectric material, it will vibrate. Okay, it will move. It will generate stress inside. And if we apply stress or apply forces on an electrical material, it will generate voltages. Okay, and typically we have in MEMS devices we have those vibration mode. Okay, so first is the most common one is fractal mode, and there is a frequency range of it. It's suitable for MEMS devices. Okay, so fractal mode is what the PMU is using. So typically we are trying to vibrate a membrane or a plate on his lens part, okay, on the longer end of it, and have make it vibrate up and down like this. Okay. Other than that, we also have lens mode, area expansion mode, and radial vibration mode. Okay, so the arrows here is showing how the device is moving and where it goes to. Okay, but for like lens mode, for area expansion mode, for radius vibration mode, you can see that they are not actually vibrating the medium, right? They move to the shorter end, which means the edge here have less dimension and it won't generate a lot of acoustic pressure. Okay, So those modes are usually not used for the acoustic mesh devices. Okay. Also, for shear thickness mode is that he is moving in the connection part. It's like a shear force. Okay, so it's also not very often to use to generate ultrasound waves. Okay, and then we also have thickness expander mode. So thickness mode is also going up and down, but just his goes like all the materials, he will go up and down together. Okay, so we call it thickness mode, and usually you can reach higher frequency with that compared to fractal mode. Okay, and also you see the surface of vibration is faced to the median, which means it can be used to generate ultrasound wave outside the device, and they can project the acoustic wave inside the median, like the fractal mode is doing. Okay, so those two are most common one for the micro machined arc transducers. Okay, and in the end we have a device which we call surface acoustic. We use surface acoustic wave, and usually it's just inside the device itself. Okay, so the wave is always just propagating inside the piezo material itself, so it draws like this. So you have wave. It could be ultrasonic waves, but it's not going to propagating out. Okay, so in this device we actually not generate ultrasonic wave inside medium too, so it will not, this mode will not also not be used to generate ultrasound waves to our medium, but it can go to most higher frequencies. So usually we will use it to do like a filter or a receiver of electromagnetic waves. Okay. So usually two vibration modes was considered in the micro machine ultrasound transducer. First is a fractal mode, and for both C-mute and P-mute we can use fractal mode. Okay, C-mute means capacitive micro machine ultrasound transducer. So capacitive means he is using electrostatic force. Okay, so it cannot generate a thickness mode because electrostatic force is not able to do thickness vibration. Okay, so CMOD we can only use fractal mode, but for PMOD some people can use it as thickness expansion mode too, if we want to have higher frequency. Okay, but here in this course we'll talk about fractal mode more, and this is because most of PMU is still working on this mode, and the frequency range is also close to the most popular applications. Okay. So for vibration mode, we just have a quick review it. Okay. If we just have a material, a piezo material itself, if one end is fixed, the other end is free, usually the resonant frequency is quarter wavelengths. Okay, so like we used to discuss about the matching layers of ultrasound transducer before, right? So for matching layer, one end is open to the medium, the other end is fixed with our active layers, right? So it's one end fixed and the other free situation. Okay, and we talk about it is matching layer, they will be quarter wavelengths. Okay, and next one is half wavelengths. If both side is free, like the actuation layers or the piezoelectric materials inside the transducer, they can vibrate it to both sides, right? So both sides is a free end for it. Okay, in this situation, the resonant frequency will be half wavelengths. Okay. And this is just an example that if we could say the piezo material is 20 megahertz, so for thickness mode, we can get quarter wavelength is probably 27.5 micrometer. And for the layer with two free ends, we have to reach 55 micrometers. Okay, and you will see this is actually very difficult. If you use bulk material, it's probably okay. But if we want to use a fracture mode, if we want to use a piezo thin film to reach 27 micrometer or 55 micrometer, it's nearly impossible. Okay, so this 30 megahertz we usually cannot reach it with thickness mode, but we can try to reach it with fracture mode. Okay, like we mentioned before, for 20 megahertz applications, we actually using fracture mode more instead of thickness mode. Okay, but if we want higher frequencies, like if we go to 100 megahertz, then the thickness will become like for quarter wave frequency it will be 5.5, for half wave is 1.1. So somehow that should be possible to reach, and this will be a selection in higher frequency applications. Okay. So now we are going to introduce the structure of the piezoelectric micro machine ultrasonic transducer. So here P stands for piezoelectric material. And we typically use the piezoelectric effect for both drive and also sensing. So we can serve as a transmitter, also serve as a receiver too. Okay. And for micro machine, as we mentioned in MEMS course, is like a technique that other than the microfabrication that makes semiconductor devices, we have some equipment or we have some technology that's going to do micro machining. Like we can go very deep and sharp etching, or we're trying to bond into different materials together. Those technique we call it micro machining. So here is what used here to the M here is stated as micro machined. Okay. It's because he is made by micro machining technology. Okay, then ultrasonic, I think we are familiar with it. It means acoustic wave more than 20 kilohertz. Okay, and typically in the PMUT, the range of between 40 kilohertz to 20 megahertz. Okay, and the transducer means there is a device that can convert energy, right? For PMOT, we actually convert the electrical and acoustic energy. Like either we convert electrical into acoustic wave or receiving acoustic wave and convert to electrical voltages. Okay, so it's an electroacoustic energy converter. Okay, and here I just show you one of the example of what PMUT looks like. So to be efficient, most of them make a circular shape of it. And sometimes we can use bonding technology to have more flexibility on make it. Okay, but here he is using he's trying to integrate PMOT on the CMOS circuit. So that's usually he will use aluminum nitride as a piezoelectric material because it's also compatible with CMOS technologies. Okay. But as previous said, aluminum nitride, the piezoelectric coefficient is not so good, so the output power of it is not as efficient as the PET material we usually use. Okay. So next is a working principle of a PMOT. Here we start with the transmit. So here it just show you how the PMU looks like. Usually we'll have a cavity here, and on top of it we have a supporting layer. Then we'll put a piezoelectric layer along with two electrodes to drive or receiving the voltages. Okay. Usually here they are not necessary to be vacuum. If some people also use air gap here, so it depends on the fabrication process and the requirement of the applications. Okay, but anyway, we need a space here is for the supporting layer to vibrate. Okay. And then for driving it, we will apply a voltage, AC voltage here to make it vibrate. Okay, so after it connected to the electrodes, you will see the material here start to, in this situation, start to expanding, and also later you probably start to shrink too. Okay, so when he's expanding or when he is shrink, it will bring the supporting layer to move. Okay, so like you have two materials, right? So top one is moving, is shrinked, which means you will bring the bottom one going to deformed. Okay, so and because this is a circular shape, so he will bring the entire, he will probably bring the entire surface up like this to make it start to vibrate, and he will probably go on in the next stage also, something like this. So it could be go up and it could be go down, and when he is vibrating, he will bring up our supporting layers. Okay, so by vibrating, he will start to generate acoustic waves and propagate it out. Okay, so this is a situation when we do transmit with PMUT devices. Okay, and reversely, we can also use PMUT to receive ultrasound signals. Okay, so when there is incoming pressure waves inside into the PMUT and then it vibrating the supporting layers, the supporting layer will also deform the piezoelectric layers too. And when the piezoelectric is vibrating, it also, when we apply stress on the piezo materials, there will be charges generated and will convert to current or voltage and radiate. Okay, so this is the receiving mode of PMUT. Currently, we have those different type of PMUT. Okay, so first one is bimorph, which means you have two layers of piezoelectric layer, and both of them have their own electrodes. Okay, so this the advantage of this is because we attach two layers of piezoelectric layer, so which means the driving force could be twice compared to only one layer of piezoelectric materials. Okay. So this is a bimorph, and the most popular one is the unimorph, which we just use one layer of piezoelectric. Partial electric layer, which means the electric layer is not cover all of them. So here is some designs. Some of the people will just cover the entire region with a piezoelectric layer. Some will expose it. They both have their pros and cons, and that is depends on how the designers like. Okay. Okay, so this is a unimorph partial piezoelectric layer, and we also have unimorph but the full piezoelectric layer. In that way, we reshape the electrodes. Okay, so like for electrode, we could only have single electrode in the middle, and also we maybe have for the electrode on the outer rings. Okay. So here it will, in the surface it will like this. This is a plate, and the electrode is on the center. And this one is we have plate, but electrode is in the outer rings like this. Okay. And some of them just combine both of them. There we'll have inner rings and also outer rings too. Okay. So Typically, the shape of electrodes here will also define which is the resonant frequency you are going to drive, because usually the shape occupied by the electrode is based on how the vibration mode you are looking for. Okay, if you are looking for the first mode vibration to be your resonant frequency, then you will put the electrode similar to the highest movement locations in the first mode. Okay, and if you want to drive with second mode more, you will put electrode to similar to what the second mode vibration is, the most deformation part of a second mode vibration. Okay, so the electrode mode will define also if affect the resonant frequency of your device. It will decide which eigenmode you are going to working on. Okay. So for inner and outer, it could be used to enhance it, because we will introduce the vibration mode later. But in first mode, you probably have only one peak. But for second mode and the third mode, you probably have 2 or 3 peaks there, right? So he's trying to have electrodes on all the peaks, all the vibration displacement peaks, so that we can have the maximum output of it. Okay. So to model in the PMUT, we actually have several different situations. First one is using the analytical circuit model. As we mentioned before, it's more quicker, because you just need using programming, probably like MATLAB, probably like C, probably like Python. As long as you can implement the equations you find, they should be able to calculate very fast. Okay. So this is the advantage of analytical circuit model. The other one is it's easier to connect different mediums. Okay, so to simplify it, when we do a PMOT, we have electrical domain. So we have input voltage or output voltage, and after after that we have a mechanical domain, right? For the vibration of the supporting layer, is a mechanical domain simulation. Okay, and in the third one is the acoustic part. So our supporting layer vibrating, then it will bring the particle inside the medium to start to vibrate and generate waves and propagating out. So in general, we will have at least 3 domains in PMOT, right? You have electrical domain, you have mechanical domain, and also you have acoustic pressure domains. Okay, it's actually not easy to put these 3 domains together using the FEM software. Okay, so maybe we can easily, even using console that are not so easy to do, you have a lot of parameters to set up. Okay, and if you are mentioned about the other FEM softwares, they are probably more difficult to do this part, and sometimes some FEM softwares are actually not very good at the connections between the different domains. Okay, so using analytical model is that we can just easily convert the different domains using transformers. Like the transformer will act like the electronic transformers inside our circuit too. It's just the transformer we put here, and it will act like the connections between electrical to mechanical and also mechanical to acoustic. Okay, so it's much easier for we to do the simulation with analytical model when we facing different domain simulations. Okay. And for the model we are going to introduce here is for thin circular plate approximation. Okay, so I think in all of the analytical model, first you have to define which is the physical definitions we want to simulate. Okay, for here is a thin circular plate. So we already assume all of the simulation we want to do is a thin circular plate. Okay, so if you come with a square plate, that shouldn't fix that the result will not be fits into this simulation. Okay, so if you use different shapes, it will not fix. Another thing is if you use a thicker plate, it probably also not able to have a good result too. Okay, so for thin circular plate, it probably usually will define aspect ratio for it. So what's height of the membrane compared to how large the diameter of your plate is will be into thin circular plate. That's usually already predefined in each different models. Okay, so when you use a model, when you find some equations, first thing is trying to locate what is the definition of its physical structures. Okay, if the physical structure is fit your assumption, then that's how you can use the model on your research. Okay, otherwise you should find the other one which is more close to the situation you are facing. Okay. And the model we are going to introduce is based on the existing model we call K-Smith models. Okay, and we just gathering a lot of literatures and trying to introduce you how to use this on your research. Okay. Second one is a finite element model, which you call the FEM model. Some people may think it's more easier to do things with FEM model because I think COMSOL is very popular, so you just need to, because it's already a commercial software package, so you just need to bring out the studies, the physics you want, and trying to combine them together and make every setup like what you need. Then you should able to get a very initial result. Okay, but actually when we use it, it's also have a lot of trick you not know, and also you need to understand all the physical meanings between all the definition behind. So sometimes FEM model is not so easy to build too. Okay, because you need to set up a lot of things, then you can precisely simulate what's your result and what is the result you want. Okay, so usually we have NCs, COMSOL, PD. For piezoelectric or ultrasound transducer, we have PD flex, and then we have Cobentor is typically for MEMS device too. Okay. Across all of them, I think COMSOL is more good at connect different domains. Okay. NCs is also very popular, but usually for single domain, it's very precise. But if you want work with several domains together, NCs may have some issues. Okay, and for Cobentor, the good thing of it is you can visualize the device. Okay, but I think Cobentor didn't have a connection with different domains, so you can probably only simulate the mechanical domains or just electrical domain, but you will not. It probably difficult to connect electrical, mechanical, or acoustic together in Cobentor. Okay. But in Taiwan, I think in for NCs and Cobentor, you can find it in the national labs. They have free software, free license for it. You just need to just need to apply for a license. You can use it for free, but for console you have to purchase by yourself. Okay, and it's not very cheap too. Okay. So generally, if you can use FEM model very familiarly, you should able to accurately design the transducers. Okay. And also, what we usually do for FEM model is we can use it to validate the equivalent circuit model. Okay. So it's like FEM model is like something you need to do a very accurate simulation, and you probably have to spend a lot of time just to allow him to compute some result out. Okay, but once you have the result out and the result can compare with the equivalent circuit model, then we can use circuit model later instead of running FEM every time, right? Then we can replace FEM model with equivalent circuit model to have a quick design. And in the final stage, after we come out a quick design, we can use FEM to double check if it's correct or not. Then it will be much faster compared to we start with FEM all the time. Okay. Especially when you want to sweep some parameters, like you want to sweep the different radius, different thickness, and also you want to try which resonance frequency can bring you the most aqueous pressure you want. Then you are not sweeping the parameter with FEM model because each time it may take you few hours or even few days. Okay, and also if you want to do more precisely simulation, you have to spend more time to do that. Okay, but in contrary, for analytical circuit model, you can run it. You can finish parameter scan probably. I think at most 10 minutes you can finish some simulation there. Okay, so it's a dramatical difference here. So usually when we do modeling, we will have these two working in parallel to help the designers to design device. Okay. So in the end is that we want to, when we have an equivalent circuit model, either we build it from literatures or we build it by ourselves. We always have to validate to see if it's accurate or not, right? So one way is to use the FEM model to do it. The other way is we can also characterize the devices. Okay. So same thing for when you use console. Here we will introduce how to use console to characterize our equivalent circuit model. Basically, we will do static and also dynamic analysis, maybe dynamic analysis more. Okay. But when we compare these two, we still have to make sure all the parameter inside is the same. Okay. Because for console, we have a lot of parameters to set up, right? And also for analytical model, we also have a lot of parameters, like the easiest one is piezoelectric coefficient. If they are different, then every simulation should be different too. Okay. So when we confirm, then we first make the parameter aligns, and then we can compare how much difference between these two, and to see if it fits if it's fulfill our requirement. Okay. So here just show you how equivalent circuit model is doing. So here we have the structures for like here we assume it's doing transmit. It works on theta mode. So we apply voltage and the P mode will vibrate and generate acoustic waves, right? And as we described, we have voltage which is electronic part. So electronic part, we can have voltage inside, and we use usually because piezoelectric material will usually behave like a capacitive impedance. Okay, so we will put the capacitive impedance here first. So this part will be our electronic domain. Okay, and after that, the energy will convert into the piezoelectric layer itself and supporting layer, which is mechanical structures. So this part here will be our mechanical part. Okay, so first we convert from electrical to mechanical. For mechanical, we will see we have a real part of impedance and also the compressed part of impedance. Okay, for compressed part is more like the dampings. For real part is like a spring factor, so like how much voltage you put in will bring how much output on the mechanicals. Okay, and the capacitance here is like a loss. Your energy was lost. Is not perfectly converted into mechanical structures and a loss inside. Okay, and in the end we have acoustic part, which is the pressure part. Okay, so when we move, the mass is also from the structure layers, including your supporting layer and also your piezoelectric layer and all the materials on your mechanical part. They will bring this one and they are vibrating and generate acoustic waves. Okay, so if we write it as a circuit model, it will look like this. Okay, so we will input voltage inside. The voltage could generate some current based on how much impedance we are faced on, and this will be the electronic part. And for this converter here, we are converting electronic domain to mechanic domain. Okay, and we have a converter. We have a transformer with a converting ratio that 1 compared to gamma 1. Right. So if we go there, which means our Vin will be times this ratio, right? Okay, and the LED can be converted into the vibrations, which is the U1 represent to the averaged vibration velocities of our mechanical part. Okay, and for mechanical part we have capacitive. We can assume there is a capacitive impedance and an inductive impedance too, and also a real part of impedance of it. So if we divide this part as those three impedance, we should get how fast our circuit plate can vibrate, right? And when we vibrate in this one, we should able to vibrating the acoustic domain, right? When we vibrating with this one, we'll bring the particles on the medians to vibrating at the same speed, and depend on how much acoustic efficient here we can transfer. Then we can bring this one will be the particle velocity. So how much will particle velocity will generate, and also how much mutual radiance is called mutual radiance impedance. Okay, so this is the acoustic impedance inside your median. How much of them can consume your energy, can consume the energy you transferred. Then after that will be how much output of our pressure is. Okay, so let's fundamental structures of all the circuit model here, and we are going to base on it to build our equipment circuit model for PMOS. Okay. So first one is for assumption here we talked about before is full piezoelectric layer. Okay, so we actually have several different kinds. Right? We can use, as we mentioned beginning you have partial piezoelectric layer, you have full piezoelectric layer. For full piezoelectric layer, you can have different design of your electrodes, something like this. You can have several rings depending on how much you like. Okay, but the final output of your PMOT can be considered as a superposition of all the electrodes. Okay, so if you see here is all the electrodes, they have different impedance, different voltage go inside, so they'll generate different current for sure, right? And they have different converting ratios for different transformers, but they all go into the same mechanical part, right? Because the mechanical part didn't change. Okay, and here you can see we put radiation impedance inside. Okay, so like previously we have this part, right? But we know this there is a transformer and there is the ratio of the transformer, so we can convert this impedance here to, we can add the acoustic impedance into our mechanical impedance too. So then in that situation, we don't have to write this part again. Okay, so it's like this. So the acoustic impedance is already converted to the mechanical impedance part. And we usually call it radiation impedance. It is caused by the acoustic domain. We just convert it to here, so it's easier to just represent the model inside. Instead of always use all of the models, we can just write it like this, so we can save some space for here. Okay. And here you can see we have a lot of parameters here. Okay. So luckily, I think you can find all the definitions, like what is a parameter presents, and you can try to read this paper from K. Smith. They should bring you all of the, they should introduce how those equations going derived out. Okay, but here we just briefly introduce that. Okay, so first one is clamp capacitance. It is from the piezoelectric material. So as you know, capacitance will affect by like how large A here represent to the radius, but here is like a ring, so you have outer ring minus inner ring times some coefficient. It's like a surface area of your electrodes, how much electrodes covered, divided by how much thickness, and times your dielectrical constant. So that's why all of them have different capacitance, right? And then of them will also have different transduction factor. The gamma here is the transduction factors. Okay, transduction factor is combined by two parameters. Okay, so first one is n here. N is depends on which mode you are working on. So the term lambda here is not wavelength. It means the mode you are working on. So different mode, the value of lambda will be different. Okay, the J here present to J is a Bessel function 1 here. So I think in MATLAB or Python you can just directly put Bessel function, then you can calculate how much n is if you know the piezoelectric efficient coefficient E31 and the ZP. We'll introduce ZP later. ZP means the length of our movement arms. Okay, so that will be the first parameter of your transduction factor. Second one is based on the electrode. So different electrode design, you will have different value of V. The N and K here present to, N is present which mode you are working on. K is like how much occupations of your electrodes. Okay. And then we go to the mechanical part, right? First we have we introduce electrical part, then the conversion transformer part, then will be a mechanical impedance part. Okay, so the number here 0 and n is usually represent the eigenmode you are working on. And Bn is the same, is a mode dependent constant. It's related to what mode you are working on here. Then we'll put different constant here, okay? And K is more like a capacitive impedance. M is more like a inductance impedance too, okay? And R is a real part of it, okay? So here you can see like if your surface is larger, then your K value will be small, right? But because it's capacitive, so which means you are larger, it's actually larger in here, which means if you have a larger surface, you will encounter more impedance compared to small surface. So it makes sense, right? If you have the same mass, if your density is the same, if you have larger width, you will need to drive more mechanical part, which means it will represent you more damping you are going to face in, and also more energy you have to lose to drive this part, right? Okay. D is I think we talked about is I think we'll introduce this later. I is the surface density. We mentioned that before. Okay. And the D here is the radiation impedance. As we thought, it will be the minimum load of the acoustic domain. Okay. So it also will be combined by a real part and a virtual part. And also, this is not a purely real radiation impedance. As we said, we need to put a conversion ratios here to make this make the impedance here to move inside the mechanical domain, right? So the impedance here are actually including the conversion values, okay? Okay. So after introduce the domain conversion part, then we'll keep going on how to generate the equivalent circuit mount or PMOD. Okay, so here we will see those the equations here are typically from the mechanical structures. Okay, so if we have a design like this in top view and in the view of the cross sections, H represent to the height of each layer. Z is the under case Z is the coordinates. Okay, so like D0 here is 0, D and D2, D1 is the layer of this. D1 is the height probably on the first layer, and so this means the coordinate of the D axis. Okay, and A is like the lateral axis, and you can also see it a length between center lines of cross-section to the location of A. Okay, and it could be represented as the radius of the inner radius and outer radius of each ring electrodes too. Okay. So if we take this typically out, is like we want to create the motion here with electrostatic, with the piezoelectric layer, right? So basically, how much the piezoelectric layer move is related to how large the voltage is. Then we can convert to how much we can use the electrical coupling coefficient here, effect, or F means effect. So we have E31 without F, and also we have E31F. They are not similar, okay? So usually when we calculate E31F is like we use D31 D31 times the Young's modulus of piezoelectric layer. This is the Young's modulus. And this is Poisson ratios, right? This is Poisson ratios of the piezoelectric layer. So this part means, because we know the Young's modulus is actually, it's looking for how much pressure. It's a pressure. The Young's modulus, the units is Pascal, right? So which means it's a Newton per meter square in the direction of perpendicular surface. Okay, but we want to convert the thickness displacement into the displacement on its length, right? Because we want to know how it extended, and how large it extends will convert to how much it can bring our supporting layer, right? Okay, so to convert the movement of the thickness axis, we have to divide 1 minus Poisson ratios to make it become a deformation on the lens, right? So here we know the Poisson ratio itself is a ratio, so he don't have units. And for Young's modulus, the units is Newton per meter square. For D31, the unit is Coulomb per Newton, right? So if we times these two, then the units of E31 effective is Coulomb per meter square. So which means it's the how much charge we can create in the dimensional, in the surface area here, right? And it will relate to how much voltage you generate. Okay. Okay. So to determine how large we can move, so first thing we want to simulate the mechanical structure. We usually have to find the neutral axis, and after that we can use neutral axis to present the entire structures. Okay. So first we want to find the location of the neutral axis here. We just add in all of the layers with different thickness and different Young's modulus to find which is neutral axis locations. Okay. So if your Young's modulus is higher, the neutral axis should close to the materials, close to lead materials. Okay. So this first we want to find the neutral axis, so we can assume everything is moved in this axis. Okay, that will be make sense earlier. And next one we want to find the fractal rigidity. It's actually similar to Young's modulus, just because we want to simulate the entire body together instead of separately, right? So we have to bring all the Young's modulus together and trying to use how the relationship between them and the neutral axis to have fractal rigidity for all the entire bodies here. Okay, and also we want to, instead of just density itself, we need to have a density of the entire surface. Okay, so we also calculate the surface density here, and also we have a length of movement arm. Okay. So it's like if you have the neutral axis will act like you start the balance point of your entire structures, right? So this will be your neutral axis, the location of neutral axis is where you start to the middle point of everything is moving. Okay, then the piezoelectric layer will generate force. So it's like your electric layer is like generating force here, right? Your piezoelectric layer here, he is trying to expanding, that will create a force here. So this is, we can assume this is a force from piezoelectric layer. Then if we simulate a mechanical structure, it will like we have a movement arm here, right? So the distance here will be the length of movement arm. Okay, then we call this length is dp. Okay, because in this model, the only thing we can create movement, we can create expansion, we can apply forces is our piezoelectric layer, right? So we just use capital ZP to present the length of movement arm, and the value will be the coordinates of the ZP, which is the top layer of the piezoelectric layer, and it minus half of the thickness of the piezoelectric layer and minus the neutral axis. So that will be the ZP here. Okay. So here you can see, you can observe one thing is the longer the length of movement arm, you actually can bring the larger movement, right? Because MP here, the movement is actually your how much force of your piezoelectric generate times how much the length of movement arm. Okay, so this is actually important when you design your piezo PMOT. Okay, if this arm is very short, then the output will typically very small. Okay, so that's why we usually have to find a balance between how thick the PMOT is, how thick the PZT thin film, and also how thick the entire structure. Okay, because as you know, if the thickness, the structure becoming thin, becoming larger, then we will have larger mass, and it could reduce your could just increase more dampings, right? But if it's too thin, then your neutral axis, let's see, if this layer here is very small and your piezoelectric is relatively thicker, then the neutral axis may move to the piezoelectric layer, and then you can see the move ZP, the capital ZP, the movement, the length of movement arm here will be super short, right? If everything already inside the piezoelectric layer, the ZP here is very small. If it's very small, which means the movement you created by the movement you create by your piezo layer is also drops. Okay. So there is always something we need to. That's why we need to run simulation, and we want to scan parameters, right? Because it's not just a one-way solution. It's not always ZP larger, then we will have better performance. Because sometimes if we want to increase ZP, we need to reduce the thickness of piezoelectric layer, or we want to increase the thickness of supporting layer. But if we reduce the thickness of piezo layer, it means the force we can generate are actually smaller, right? Because the larger the thickness, you should bring the larger charge, which usually can create more deformations. Okay. And also, if we bring thicker supporting layers, it will also make the entire structure become thicker. And if we want to maintain the same frequency, we have to increase the dimension of the entire device. Okay, so the cost layer is hard to calculate just by one of the factors. That's why we have to run a complete parameter sweeping with that to find the best performance of our device. Okay. And here we just introduce about different models. So the most popular three models we usually looking for is mode 01, mode 02, mode 03. For 0 here means the center will be the highest vibration part when it is vibrating. Okay, and followed by 1, 2, and 3 mode. So usually, if you just hear people say mode 1, mode 2, mode 3, it's actually present mode 0, 1, 0, 2, and 0, 3. Okay, because in the perspective of generating acoustic waves, usually the center part, the higher the center part, you should have larger displacement and larger acoustic pressure out. Okay. If we work on the mode 1.1 or 1.2 something, it's more like you have two peaks. Sorry, it's not like it's like in the center, it's not peak. So it will, in the cross section, it will work something like this. Okay, so your peak is in somewhere different location, and the center will drop. So the pressure output here will cancel interference itself. So the acoustic pressure from other different modes will be comparatively should be very weak compared to mode 0, 1, 2, and 3. Okay, so sometimes if people just briefly said mode 1, mode 2, mode 3, you can think it as mode 0, 1, mode 0, 2, and 0, 1, 0, 3. Okay, so we can actually using based off different order of Bessel functions to present these ideas here. Okay, and then you can find different mode. You should count two different lambda values. That's what we mentioned before. Okay, like here you have different lambda value here, and you can see it's all start from 0. Okay, so it means it's from 0 and n mode n is probably 1, 2, 3, or maybe more. Okay. So different mode, you put different lambda value inside. Those things we'll introduce later. VN, I think we also introduce here, right? It's the ratio, it's the parameters on this side, so you can calculate it here, or because it's dimensionless, so actually you can just put a number inside too. Okay. So this table, when you really do the simulations, you can take a reference, so you don't have to write all of these inside your equation, inside of your code. That will be make things much more easier. Okay. So here we introduce. It will be our primary part. Is we'll introduce this circular model. It's typically for one electrode in the first mode, which is mode 01 we said. Okay. So in this situation, as you can see, we have electrical domain, mechanical domain, acoustic domain. So we have input voltage generated the current. The converting ratio is given here, is equal to, there is a constant here times the E31 effective. E31 effective actually how to find? You can find this. You can find this E31 in the console. Then you can calculate based on the equation we previously mentioned. Yeah, you can calculate D31F with these equations. Those values you can all find, so you can compare each other. And also, if you have real device, you can just measure D31 and calculate it back. Okay, and VP will be the length of movement arm we just mentioned. V1 is a ratio based on your electrode occupations. It's also a constant that you can find in the references. Okay, so gamma 1 here is you can know what's the value it should be, depends on your material, your stack, and also the electrodes. Okay. And the C0 is, as we mentioned before, you can calculate by this one. But because your V in here is actually directly be reflected to this one, right? Here you don't have any impedance here, so you can just assume V in times gamma 1 and it goes to mechanical. Typically for C0, you probably don't have to calculate it. Okay. Then we move to mechanical domain. You have capacitive impedance, real hard impedance, resistance impedance, and the inductance. Here we all give by these values, so you can directly calculate the value of K1 and M1 by A is the radius, D is Richter flexibility, and the pi is the circular ratios with the parameters here. Okay, so I think the only thing is I actually have different definitions, and you have to make sure this assumption is close to what your console provided. Okay, so you can assume it's 0 in the beginning, but you need to confirm it with console to see what happens here. Otherwise, your simulation will have to compare to. Okay. So your voltage after a conversion factor, you should get a mechanical velocity. Velocity here will act like a current. Okay, it will probably a current style here. Okay. Doing current is to make it easier because here you have impedance here, here, and here. So if you want to directly convert the voltage to this side, you need to do a impedance partialment to have a partial voltage at this side and convert to cool domain. If you use current style, then this one can convert directly from the conversion ratio of the current and it goes to the other side and it becomes acoustic particle velocities. Okay, so the capital U here will be your particle velocity. Okay. So this is actually acts exactly like the models you can have in your circuit, like electronic circuit. So you have converters, your converting ratio, transformers, and you have all the impedance, how the impedance is defined. Then we're supposed to know how much voltage will comes in. Then we can have how much mechanical velocity, how much particle velocity, and how much pressure can go out. Okay. In the reversely, if it's receiving mode, its pressure comes in, we should have voltage out too. Okay. And here, I think the only thing we don't have here is impedance for the acoustic domain, which is R1 and LR1 here. Then we'll do it in the next slides. Okay. So for the acoustic load, which is the impedance of acoustic domain, we use a circular piston approximation here. Okay, so again, what is the difference between piston and the membrane? Okay, so for piston, everything moves together. Okay, so the entire things will move together. Okay, So all of them will have the same mechanical velocities here. We call it piston approximation. But as you can see, what we have is a membrane, right? So membrane actually vibrated something like that. If we fix two sides, so in the center we actually have higher velocities, and in the edge probably not moving if it's clamped. So the velocity is not always consistent. Okay. So that's the averaged velocity. So in previous slides, here we call it average velocity instead of just velocities. Okay. So here we introduce a piston approximation first, but actually in real case we should not use pistons simulate our pinwheel device, okay, because it's not a piston. Okay. To be easily introduced, we first talk about piston approximation first. So here we have a definition of acoustic domain impedance is your pressure divided by your particle velocity, and in the mechanical domain, your impedance is force divided by how much mechanical velocity we can have, right? And usually we can write as acoustic radiation impedance as real part and virtual part. The real part can be calculated with the equation corresponding to the Bessel functions, and the virtual part also. If you draw this out, it should look like that. Okay. So if the frequency is very high, you can summation like this. If the frequency is if it's very low, you can have this assumption. Probably is close to this region, so this is k is equal to k is a wave number equal to 2 pi f. I think we introduced it could be 4, right? K is 2 pi f, or you can use as 2 pi over lambda. Okay, so the higher, if we go this side is higher frequency, this side is lower frequencies. Okay. And you can see if we go to the higher frequency part, our compressed part is actually close to 0. So here we just use the real part impedance to present it. Okay. But it will also depends on your radius too, right? So the value here, 2K, which region you are in, your device is in, will depends on how much frequency you have, and also how large the device you have. Okay, so if your device is larger, also you go to the region that the compressed part impedance is smaller, and the real part is dominated part. Okay. Then we will introduce radiation impedance for clamped membrane, which is more similar to the PMOD, right? Because the previous one is a piston, which means every unit moving together, but that's not happened in the PMOD. Okay. So for the simulation here, I think the equation is more complicated, so we are not going too deep there. Okay. We just don't know the concept is the impedance on a membrane is not uniform, okay? Because as you can know, our impedance, if it's acoustic impedance, is related to your pressure and the particle velocities, right? If it's mechanical impedance, it's force versus velocity too, okay? But right now is everything different. Is the velocity here will be different. And so we cannot expect the pressure is also changed to maintain the same impedance here, right? So typically in different location, we should have facing different impedance, okay? So similarly, like if you running in if you running in a swimming pool, the faster you run, you should have more. You should trying to conquer more forces from the water, right? The water will trying to stop you running inside. But if you run faster, you encounter more forces. You encounter more impedance. If you run slower, then you will encounter less impedance too. Okay, so that's the concept here. Is the radiation impedance in the membrane is not uniform distribution, unlike the pistons. Okay, so we can define as like something like this. Okay, so it's actually reversed proportional to the reference mechanical velocities here. Okay, so in the model we will provide you, it's using the far field simulation approach. It's based on the Baukamp's impedance theory. Okay, I think we will attach the reference and you can find how it looks like. But usually it's computed with this pattern, and it's also including the radiation directivity too. Okay. So basically, inside the paper, he provides a table for us, so we can just use the paper to find the different ratios. There's the dimensionless factors to separate your. No matter how large your device is, you can adjust the values from the table inside your device to simulate the radiation impedance. Okay. So if you look at the sample code, you should know what it's doing. Okay. So here is just to compare the difference between the pistol model and the current model. Where is the radiation, the difference of radiation here? Okay. So you can see both of them are actually, when you're looking for high frequency range, the complex part, imaging part of your impedance is actually managed. But for membranes, usually if it's the same speed, the membrane should encounter larger impedance compared to the piston models. Okay. Then we'll quickly go over something that you already know is the resonant frequency. So the resonant frequency is also similar to simple harmonic, the equation of simple harmonic 1. Okay, but just replace the spring constant K as the mechanical parts. Okay. And lambda is still related to what mode you are working on. So like, if you remember previously, lambda is 3.996, which is for first mode, right? The number square of 3.96 will be 10.22, which this values is coming from. Okay, so here is F0 means it's a first mode. Okay, so if you know the Young's modulus, you know the surface density, you know how much mass in your structure, then you know lambda here and you know radius, then you can calculate the resonant frequency very quick with these equations. Okay. Also, if you want to calculate the frequency includes the acoustic load, you can use the equation here to consider the load effect, because you know the AE is transformation ratios between acoustic and mechanical domain, right? And if you remember, when the transformer, you have A1 here, but if you want to move this to this side, you want to move the impedance here, you have times the square of it. Okay. But anyway, at higher frequency, most of the time you will just ignore this part, okay, because this the impedance from the mechanical mass should dominate your models. Okay. So next one, we will just introduce how to use this circuit model to calculate things out, and then we'll probably introduce the example code next week. Okay. So first is the transmit mode, which is our example code is bringing, is how to have the output pressure here. Output pressure means is actually happened. Pressure is like voltages, right? And the acoustic, this is a particle velocity, is like current. Okay. So pressure we measure, which is actually the real part that we put on the impedance, that will be our real P out. Okay, so P out you see here is actually, if you go from V in and you times V in times gamma 1 and you go this side, and because you want you have two ways to do. One is to calculate your mechanical velocity by divide by U1 with all of those. Or the other options is to do a partial voltage difference, right? So here we choose the first one. Is we're trying to, if we move to here, so we trying to move if we in and the gamma 1, and we want to find how much U1 is. So okay, we already write here. Okay, it's gamma 1 divided by those impedance here on this side, which is at 1. Okay, and also we want move, so this part will be here, but we want to move this part goes here, right? So we actually divide by this times, this will be times the square of AE square inside here, and then we move it out later. Okay, so typically it's impedance from the mechanical plus the impedance from the acoustic. Okay, then we can get how large U1 is, and after U1 and the conversion value, which means the capital U1 here is equal to U1 divided by the under case divided by our AE1, right? Okay, so that's how this equation is coming from. Okay, I'm just trying to make it cleaner. Okay. So if it is in the resonant frequency, you can eliminate those frequency part, so you can have R1 times, in this time U times AE1 together, they will go up. It looks like this. Okay, otherwise you can just use this 2%, as I said, is gamma 1 times V in divided by the mechanical impedance here, divided by what you moved from the acoustic impedance side, and the times the transformer coefficient. Okay. Okay, so in this way, by this equation, you should able to calculate the output pressure based on the input voltage, right? I think we missed one part, is after we have a particle velocity, what you have to do is to times the real part of acoustic radiation impedance, then you can get P out. Okay.